Okay. So we're talking about the selectivity between E and E versus Z, the isomers in Kumada coupling reaction. So here, if I am starting with this A, which is this one, vinyl bromide, and this is another partner which is methyl Br, right? So here we are taking these particular systems where if you see this is a transform and this is a system where we can create it E and Z. So it is E and Z. Now we have a mixture of these two and it is in a ratio of 2 is to 1. One is major and one is minor. These are the reactants that we are talking. Now, when we take this A plus B into is to 1 ratio, and then the coupling partner is taken as equal as your A, that means two equivalents of A is there, then two equivalents of our coupling partner is also there. That would lead to the formation of only exclusive product, which is major in nature. That means only the trans product is going to form, the cis is not going to get reacted at all because that mechanism does not allow. So this is the beauty of the system that even if we have a mixture of isomers, cis and trans, the major isomer will lead to the product formation. And in this case, this isomer will not even react with the Grignard reagent. Now, so this was all about the Kumada coupling, where we have seen that organolithium or Grignard reagent in presence of the palladium catalyst that helps in forming the CC formation and uh, it follows the transformation. It prefers to have a transformation, and then the major isomer will give the major. Now we have a Suzuki coupling. So as I said, that based on the coupling partner, the name of the reaction is different, and with little additional additives also. So it involves an organoborane. So earlier in Kumada we have a organolithium or region. Here it is an organoborane compound, and besides that, there can be use of a nickel catalyst instead of the palladium catalyst with some additive as well, which is generally a base. So let's see. We have a RX, which is again the similar scenario what we saw in Kumada, and we have an organoborane compound where the R dash is going to coordinate with your R. Now here nickel catalyst or the palladium catalyst or the base. So here, depending on the different groups that are coordinated to the boron, the names are different. If we have a Br2, it's a trialkyl borane. BF3, it's trifluoroborate. BOH2, that means boronic acid, and Br2 is boronic ester. Now, the additive bases that are being used and why it is being used. So we have a base which is generally a nucleophile like NaOH, NaONe, Fe minus. So what it does, it actually attacks onto the boron because it's a Lewis acid. So this is Lewis acid, right? The boron is having empty orbitals. So it comes and attack over there and therefore minus charge on comes onto the boron. Now this is more reactive carbon ion to give this R as R minus because again the boron will come into its three coordinated system rather than being in unstable four coordinated. So this is very, very useful for the transmethylation step. Now, bond formation between the two alkenyl centers. So here, if you see, we have this three isomer where we have this double bond, and here and this is the partner. If you'll see, this is the Br2, which is the organoborane compound. This is the partner that will be connected to the other one. And here we have a alkene, which is a halide system, the leaving group. So if it is maintaining here Z isomer and here E isomer, it is going to retain its stereochemistry as what is maintained over reactant and the partner. So what we saw that there was a new bond formation between these two. This one, this new bond is being formed. This is a new bond. And here, this side, the Z isomer has been maintained, and here the E isomer has been maintained. So both the stereochemistry has been retained. Now, why Suzuki reaction? It has been found that it is better than the Kumada. Why is it so? Because Suzuki reaction involves this, we know that Suzuki reaction involves the organoboron compounds and Kumada involves the Grignard reagents. So Grignard reagents is also having a problem with the functional group because they are highly reactive. They are nucleophilic in nature. They cannot just stay for looking at the functional group to be staying as it is. They can't be just spectators. They will react with the system, and then there would be a problem in having the desired product. For example, if we have a reaction where we have an acidic group over here, like esters or some acid is there, and this is the leaving group. If you are using borane compounds, then instead of OTF, AR will come, there won't be any problem. But if I'm using an organolithium or granulate reagent, these CO2Me or CO2R group, it also get affected by the uh, this Kumada reaction. So this is one example. Second is the carbonylative coupling. If we have this halide and this is an organoborane compound and carbon monoxide is there, it would definitely give us an insertion of CO and there would be a ketone formation, or you can anyway say it as the carbonyl will be inserted over there. This carbonylative coupling is also not possible in case of the Kumada. So there are two differences with the Kumada than in Suzuki. Now the third reaction that we have in hand is a negation reaction. In negation reaction, now the difference is earlier we were using in Kumada, we were using the organolithium or Grignard reagent. Here it's also Grignard reagent, but it's a zinc-based Grignard reagent. So zinc is less neutrophilic compared to the R lithium or the magnesium. Based on that, it has a good function group tolerance. So if you don't want to use Kumada, you can better go for this one because it is having a tolerance compared to Kumada. So Kumada reaction also fails in ketone synthesis where negation reaction works. Say, for example, if you have a RCOCl and if you're using this one, butyl will go and connect it. This is the desired ketone, which will not be happening in case of the Kumada because the R lithium would go and attack onto your ketone and that would ruin all the system. Now, the another coupling reaction that we have is still a reaction. This involves organotin compounds as coupling partners. Every functional group can be tolerated here, and this reaction is mostly performed by academicians because the thing that is being used over here, it is toxic in nature. That's why it is not applicable to the industry. So it is highly toxic. So it's only applicable for the academicians. But it is having a beautiful applications because it is widely open for all the functional groups. So here R is also not just the aryl or vinyl, it can also be used for the alkyl substrates. And similarly, on the other hand, and it will give you the RR dash. Now here we have a dihalide system. If you see Cl and Cl, and here we have SNME3 and double bond. So this part and this part, since we have two coupling partners, it can easily combine with both of them. And here, if it goes from this double bond O and forming here and the other part also, it will give you a product as a 62% yield. Now here, this also undergoes a carbonylative coupling where we have addition of CO, and in presence of that, it would give you a C double bond O, which is a ketone over here, of course. The aldehyde synthesis is also possible in this case if we are using a tin hydride. Generally, we were using R10, but here we are, if we are using a tin hydride, that would give you aldehyde synthesis. Just a moment. So as you said, as you saw, like earlier, it was R, which can be alkyl, which can be aryl, which can be vinyl. In this case, also now here it is R equals to H, which is your hydride system, and in that case only we will be able to get aldehyde, which is not possible with other substrates. And aldehyde synthesis can almost be only be seen in case of the Taylor reaction. So when reaction with alkyl electrophiles as the substrate, so when we have an alkyl electrophiles, now generally we were seeing that it was an sp3 system and it was generally a sp2 system and not sp3 system. So breaking this bond is also a bit difficult. So what really happens when we are breaking this, the palladium zero is there, it will undergo firstly, the breaking is difficult. Secondly, when it is undergoing an oxidative addition, which we have seen over here, there is a beta hydride present over here, and that can come and get eliminated and it will form an alkene. It will not give you the desired product. So in this case, when we have this kind of system, it would come inside this and it would release as double bond. So this is the new olefin that would form and not having the desired product. In that case, what we can do to avoid a beta hydride elimination in alkyl substrates, we can use a bulky ligands in case of the palladium. Like bulky ligands, meaning that palladium is highly spacious, highly hindered by the bulky ligands. So there is no chance of having a beta hydride elimination to occur. And in that case, we can get our product easily. So in this case, there's a limitation that only primary alkyls can be used, not the tertiary and secondary, because the oxidative addition actually follows the asymmetry mechanism, whereas it is not possible in case of the secondary and tertiary. Now, if you'll see here, if you have this example where we have given a stoichiometry of the stereochemistry of the D and deuterium instead of hydrogen, And when we are treating it with PHBr2, we'll always see that one of the D will be changing its stereochemistry to inversion because it is following the asymptote mechanism. So this is only possible with the 1 degree. What is the better solution with 2 degrees and 3 degrees, like secondary and tertiary? We can use nickel instead of the palladium because it is prone to react with electrophiles via radical pathway, where the radical pathway is not suitable for the palladium system because it follows the asymptote. So if we have a 2 degree BR, here we have used nickel Cl2 in terms of the base, it would form the desired product, and the ligand over here has to be bulky because again, the problem here is like it should not undergo any kind of system. Now the last part of the thing is like asymmetric stereo convergent Suzuki reaction. So here we have a stereo center and it is having a racemic mixture. That means both RNS are there and we are using a Browning ester in presence of the nickel system. What really happens is it would give you one product like 99%, 90% enantiomer selective, and the ligand actually is directing your stereo conversion. Like it is, even if you're starting with a mixture, you will always get a one product. And say, for example, we have a RNS both over here. It, since nickel catalyst is going with a radical mechanism, it can always attend the new coming partner in that one direction. It can't be coming from the other two directions. So therefore, it is called as a stereo convergent asymmetric synthesis. So this is the week two system which we have covered. So please go through this one more time. We have 2 more minutes, and have the then we'll have the week three list. So these were the certain problems that we discussed in our week two session, where the first question was the role of borate anion in Suzuki coupling. As we know that why the borate ion was important. If we just use the organoborane compounds, they are Lewis acid in nature. Uh, in that case, that means it is having a deficiency, so they cannot transfer the R as R minus, which has to coordinate with the palladium. So with the transmetallation step, there has to be R minus, which can only be possible if it is being treated with a base or a nucleophile, which generates a negative charge onto that system. As you can see over here, when it becomes a B minus, having a 4 coordination, now the R dash, which is going to transfer to the other species that would have the minus charges, it is very, very easy and the reactive species to interact with your palladium X. So therefore, it acts as a carbanion transfer agent. The second question that we had, like we need to identify the steps in the cycle and predict the name of the coupling reaction. As we saw that firstly, palladium 0 is going to palladium 2 with the interaction of R at X, which is an oxidative addition, followed by when we have an RMG axis. Mg means that it is a Kumada reaction because it is either involving a organolithium compound and organo magnesium compound, which is called as Grignard reagent. Once it is involved in this step where it has taken the MgX from the palladium and it has given the R double dash, that means it is undergoing a transmethylation followed by rearrangement, and therefore because it is in a trans conformation and then it has to go to cis. Only reductive elimination can only occur in case of the cis formation. It doesn't occur in trans to cis. Trans rearrangement has to happen, and therefore the last step is reductive elimination. Third is the major products of NB in the following sequence. So this also we have taken in consideration. We have an alkyne system over here, and we have a organoborane system. So firstly, when it reacts with this one, what really happens is a hydrogenation step because that unsaturation in the alkyne that would help in getting saturated by using a hydrogen boron bond. One hydrogen will go to one side and boron will coordinate to other. Hydrogen would go to the side where it is having the n-butyric mode and stay over there. And once it is being formed, since we are using water, so this can easily be cleaved and therefore forms a BOH2 that's called hydrolysis, and that would give a catechol. Once this BOH2 is formed, this is a new partner, a coupling partner for the system, and we have a bromine. And since we said that it retains its stereochemistry in which form, like easy form it would be formed. So the answer fourth would be the right option. So the following reaction Pencil system and AR2I. Now here, if you see, we are starting with inversion and like one type of isomer. It is retaining that it is generally called as stereo conversion. Even if it is racemic and it is giving you certain type of system, and therefore it would give you a stereo conversion. If it changes the stereochemistry, that it causes stereo diversion, and if it is very stereo specific, like okay, from this it has to give you only the one type of isomer that is called as stereo specific. That all examples also we have seen. So find out the suitable A in this reaction. Now here, if you see, we are having an instead of I, we are having an aldehyde group. This is very, very specific that we know it can only be possible when we are having tin reagents, which is having the hydride, because here this HBH2 can't react because there is no base and only the carbonyl group is there. Until this base is there, sorry, until this base is there, it will not react to give you any hydride transfer. So the A and D options are anyway gone. The B and C option, if you see tertiary butyl and hydride, only the hydride is the one which is going to transfer over here and forms aldehyde. So option C is correct. So with that, yeah, the last question we have, which is the following statements are true if we are using an alkyl halide system, which is the sp3 system, and whether it would form or not. So this is an sp3 bond formation, which is here, which is correct statement. If ligand that is being used to coordinate with palladium is PME3 with palladium acetate, then reaction is feasible. I don't think so. Why? Because it is having a tendency that it undergo beta hydride elimination because PME3 is not very hindered. But instead of PME3, we are having a very bulky system like cyclohexyl groups are there with phosphines that it would restrict the hydride L to be eliminated, and therefore this kind of formation can happen. And the last statement, it undergoes beta hydride elimination if PME3 is used. So last statement is also correct. So with this, our P2 session is also over. Then now we can quickly see the extra class week 3 that we have taken yesterday. Please go through the questions one more time. If there is any doubt, please let me know. You have a 1 minute time and then you can start. Thank you. Okay, so if there is no doubt, then we can start with the session. Uh, let's firstly look into what we have right in yesterday's class. So we basically focused on to Sonobuchira and Heck reaction. Uh, let's start with the Sonobuchira because here in Sonobuchira reaction, we were treating the Rx where R is aryl and vinyl. And Sonobuchira is basically for the alkyne substrate. So as I was mentioning that in earlier, if we see that so in earlier case, when you were talking about, so they were named reactions which were having Kumada, uh, Negeshi, so, no, Suzuki reaction, Chili reaction, then I think we did it this way. Then we were having Sonogashira reaction and the Heck reaction. So here basically if you see the generally we were using the in this one we were using organo, lithium or magnesium, the metal was involved. In Negeshi, it was organozinc. Suzuki, it was organoboron. Chile, it was tin. Right? So these were the, but in case of Sonobuchira, it's an alkyne substrate. And in Heck, you will see it is an alkene substrate, which is very specific now. So again, the names are varying with respect to the coupling partners specifically. And the palladium is bit constant over here, but if you see here, the organo systems with the coordinated with the lithium, it is coming as an R minus. But here we are talking about the alkyne and alkene substrate. So it is very, very important to understand these things, please. So first, when we have seen the Sonobuchida reaction, you can see it is reacting with terminal alkyne and it would lead to form the internal alkyne. There is no coupling center over here, like any metal center is not involved over here. But only good point here, we need to remember that besides the palladium catalyst, we have a co-catalyst which is copper X, which can be copper Cl, Br, iron and base, which is stoichiometric in ratio. So if you'll see the mechanism of the Sono-Kishida reaction, it starts with the palladium zero, which is active, and first it would be having oxidative addition as it is forming with all the CC coupling. Once it is done, then what is the role of copper X over there? What really happens is we have terminal alkyne, the acidity of that proton that increases when it is in contact with the copper X, and in presence of the base that the interaction of copper X with the alkyne that makes the proton very acidic. And once it is acidic, it can be taken away by any normal base. So we have used an alkyne, trialkyne. Once it has been used, then it would go as NH. That means nitrogen has been protonated with a loss of X minus, giving a salt form, and therefore making a more reactive alkyne, which is connected to the copper. So if you'll see here, the minus charge will be more compared to this one. Once it is there, then now the transmethylation can happen. Copper can easily take the X and regenerate itself, and therefore C, triple one C, R dash is coordinated now palladium. Now, the regeneration of copper X makes sense that it is acting as a co-catalyst. It is not something which is used in a stoichiometric amount. Once this is done, then when these two things are in cis formation, cis nature, then it undergoes a reductive elimination to give you the desired stuff. So first step is the oxidative addition of the RX prop. The second step is the transmethylation, where we have already told about that nature of copper X is required, and the reductive elimination. Now, in case of dihalides at substrate, so when we have a case of dihalides, and it is this kind of system, and when we have an N-pentyl C2one CH, palladium cation, and copper I. So firstly, it would react with one of the Cl, and therefore it would give you this product. And the other part, which is going to react with the methyl trimethyl alkyne, then it is going to react on the other side. So both the dihalides are going to get reacted and substituted. Now the next part is the head coupling reaction where we have RX and alkene. Now here it is alkene the substrate, which is very, very important. And R dash is going to transfer and forming an alkene bond over here. The new alkene would be formed. Now here the palladium catalyst and a base again. So here it is applicable for aryl and vinyl. So we'll start with the Ln palladium 0, which is active state. And after that, when we have a palladium, when we have Rx, it would first undergo oxidative addition. Now, since we have an alkene, it would undergo the coordination of alkene. The coordination of alkene will remain as such, and then there would be an insertion of R group to the alkene. So once this happens, and we see that, okay, there is an alpha, there is a beta. Alpha is the center which is connected to the palladium, and the beta which is connected to that alpha center. Now, when we have a beta hydride elimination, chances it undergoes a beta hydride elimination, therefore forms a new alkene, which is in coordination with palladium. Now, in presence of base, what it does, it takes up the proton and X releases as a salt, and therefore we get the Ln palladium 0 and our new desired olefin. So here, as I said, the number of the steps can be increased, but the basics of that is oxidative addition, transmetallation, and the reductive elimination is constant for all the coupling reactions. In this Heck reaction, there's two more steps. One is the coordination of olefin, insertion of the olefin, and the beta hydride elimination. Here, the transmetallation is not there. Now we have a Heck reaction and the related rates because it's very important, bit complicated also because we are treating it with olefins and the olefins are having the chances like, okay, at one point it can substitute, other side also it can substitute like this and this. Here there is no substitution is having the higher rate. When it starts getting substituted with the electron withdrawing group and the methyl and the phenyl, the rates gets decreased. We'll explain it a bit later. Then we have a rates of the ARX. When we are talking about the aryl halide, that X can be your diazo, and positive iodo, triplet, boron, bromine, and Cl. So this is having more rate compared to the iodine one. The region selectivity, like at which region, like we have a two centers where the substitute can come and attack over there. There are two points where we can have it. So if we have this kind of substrate, so because it is having CO2 Ne and this side there is no substitution, then 100% at this position only it is going to have this phenyl group. When CN and phenyl, the same thing. When we start getting this way, like it is only having one side substitution, other side is having H. Now 80% chances to have at the side where there is no substitution, and the 20% is like where it is having one substitution. And here when it is having two ways substitution, like similar like methyl and CO2Me, we will choose the center where it is having less electrophilic uh, um, uh, center, like meaning at this center it would be more delta negative because it is taking the electron. So this alkene would go like this with delta minus and delta positive. So when the delta positive is there, the other delta minus, which is going to come and attack over here, it would always prefer to attack here rather than this one. We'll see in the mechanism. So less substituted olefin, it is having more reactivity. More electrophilic C center gets a substitution in higher rate, which I just showed. The C center, which is far away from the electron withdrawing group, that is good. That would be having more reactivity. So here, now the next case that we are looking into, here we have the two centers and here only one ONUM is there. But since it is highly substituted, we prefer to have 100% over here. At this position, again, 79-21, when they are cis in nature, then 93 and 7, then we have this kind of system 90 and 10. So it is very feasible to see over there. If you see carefully, here it was ONEOM is having high electron minus I charge, whereas it is one being replaced by Me now. So that's why the percentage of attacking at this position is 10 compared to the other one. So if we have this kind of system where we are taking the phenyl bromide and this is our olefin that is going to coordinate. Now we are saying that this is not having any substitution, so it should be having 100%. Why? Because here, if you'll see, now this position is less hindered and that phenyl can easily come and attack over here and it maintains the transitory. It is always a system that would prefer this kind of stereochemistry. Here, if you'll see, if I reverse the sides and the less substituted or the no substituted is away from the phenyl group, the insertion of this phenyl at this position is hindered because it is having already a phenyl and a methyl substitute attached with the CH2. It will not let it to come and attack over there. So there is a minor chance of having this product. Now, when I was talking about why the electron withdrawing group should be a part or the center which is connected to the electron withdrawing group, there the insertion can't happen. The electron factors are such a way that palladium is having positive charge because the negative charge is coming from bromine and the phenyl group. Similarly, the alkene would be having a charge separation. The one center which is closer to the electron withdrawing group that would be having minus because the electron withdrawing group would be taking the electrons from that particular center. So it is meant to have more electron density of the olefin towards it. So it becomes delta minus and it is delta positive. Only the delta minus and delta positive can connect or interact with each other to make a bond compared to the delta minus and delta minus because of the repulsion factor. And as I said, that it always prefers to have a E product, which is ARX, and when it is connected to the bond, and then it would form a E isomer. Here also, if you see at this position, it has to form, it would prefer the E isomer. The mechanism, like we have a ARX and ARRR, then if it is following any position, like, okay, at this position, AR has coordinated. When it is coordinated or inserting the olefin, it is in plane as that of the palladium. Now, when it has to undergo the reductive elimination, the firstly the hydride and the palladium has to have in same plane for the beta hydride elimination to form an olefin bond. That's where the rotation happens, and the hydride and the palladium comes in same plane, and AR comes in above the plane as that of the R, or the vice versa. And these two R groups, which were in the substrate as a cis position, that they become strands, and therefore uh, at the end we end up getting a product where it would be like R here and the other R here, which is in trans position. So stereo selectivity, if we have these two centers, and here it is referring to coming E isomer as I mentioned. But if in this, like in this particular case also, we have P double bond CO2 Me, it would prefer to have this particular center as in E isomer, and pH would go to cis, that it would go inversion. Whereas in this case, if you'll see, it is having already an ethyl group, and the coming group is like phenyl group. This is thermodynamically stable. It can't go undergo rotation very easily because that would be then very hindered. So it prefers to get the phenyl group in cis to this particular geometry and retains its, even though the product is being formed as same as the early reaction, but if you see the coupling partner, it is different over here. So we also need to see like what is thermodynamically favorable in this scenario. Then we have heterocycles. Mostly here also you can see that we have a heterocycle, and instead of running this particular center has to come, that would form that it means it does a reaction with heterocycles. And asymmetric reaction, we will get a one particular stereoisomer with a high enantius level. So with this, our week 3 lectures are also over. Whatever the rest the lectures are pending, we will cover it in our last session where we will see the assignment problems also. Let's quickly look into the problem session where we have to match each of the following named reactions with the correct metals, at least in the coupling partners. As I mentioned that we have a Suzuki. Suzuki involves the palladium and the boronic acid. So option A is correct with palladium. So you have to choose both of them. Heck also involves the palladium, but it involves the alkene. So the part B. Kumada involves the magnesium or the palladium. Palladium as the catalyst, but it involves the this Grignard reagent. So option 3. Then we have Nigeshi. Nigeshi involves the nickel, and nickel, with nickel it involves the organogen compound because it undergoes also the reaction with the tertiary or secondary alkyl halides, and it follows the radical pathway. Sonogashira involves the alkyne as the substrate, which is this terminal alkyne, and it involves the palladium. And the second question, which one will be the product of this reaction? As we already know, that dihalides in presence of this nickel can easily undergo the reaction and the disubstitution can happen. So this is straight away the product for this reaction as it retains its chemistry. So it is easy that OPH is the leaving group and it easily goes out. And this is the product. This is the substrate that is going to come and attach to your center. Then the next question was like, what is the role of copper iodide? As you mentioned that it is acting as a co-catalyst, it helps in transmutation. It also makes that alkyne proton more acidic for the transmutation step to be even more faster. And what would be the product of these reactions that we saw? In this case, it would be in transgeometry. And in this case, where already we have a substrate and it can't undergo the change in the stereochemistry. So therefore, it would prefer to have the new coming substituent attacking onto the side where it does not has to undergo the rotation. So with this, our problem session, all the 3 lectures, we have summarized and we have revised it again. I'll wait for 10 more minutes for you to come up with any questions or any queries if you have feeling any doubt, so that it would be easy for compiling the session in our next Saturday and Friday. Thank you for joining, and I'll wait for you to post any question or ask any question. Thank you.